So today we're going to take a look at what is known as electromagnetic radiation. And when we study and take a look at electromagnetic radiation, we're going to notice that it's going to travel in the form of a wave, which means that we get to look at some of those concepts that we've seen in conceptual physics, such as wavelength, frequency, and also the energy associated with the actual wave. Not tomorrow, since I don't see your class tomorrow, but the next time we meet, we're going to talk about this thing also known as an atomic emission spectrum. This is really cool. The reason why this is cool is we're going to see eventually that every single element has its own unique either fingerprint, if you want to think about it as fingerprint, or you can think about it like it's DNA. And one of the things that we can do is by studying this atomic emission spectrum of looking at light, I can identify elements based upon this spectrum, like its unique fingerprint. Also, we'll talk about how they're able to look in distant galaxies and say, oh, in that distant galaxy, I can detect that, hey, there must be the presence of oxygen. Oh, there's also carbon in that distant galaxy. Oh, maybe it can have organic life because I see those elements and they're light years away in this case. It's all coming due to this atomic emission spectrum. So that, I guess, will be something we'll look at after the Easter break. Here we go. What we're going to talk about today is we're going to kind of come back to this orbital diagram. And we're going to take a look at the element hydrogen in this case. And one of the things I know is when it comes to hydrogen, that it has its electron in the 1s sublevel. So it's just sitting down here. And the reason why I know it sits down there is because of that thing right there, the off-ball principle. Off-ball principle simply says the electron has to exist at lowest possible energy. Now, we also have this term known as the ground state. And what the ground state is, it simply says that, hey, when the electrons are actually shown in their lowest possible energy, then we can say that the electron is in its ground state. Now keep in mind, every orbital diagram that we build, we will always have the electron in its lowest possible energy. So we're going to always say, oh, those electrons are in their ground state. But one of the things that we're going to see is that we can get the electron to come out of its ground state so long as we give it a quantum of energy. And remember, if we give it this energy, and it's enough energy to take it to one of these given sublevels, the electron will promote up. But keep in mind, if I give the electron some energy, and this form is going to be called a quantum, and say that energy takes it to this point right here, remember what's going to happen. The electron is going to say, no, thank you. I will not accept your energy. I'm going to stay right here. I will not transition unless you give me enough energy to go to one of these specific sublevels. And if you remember, we said that because the electron can only exist at very specific energies, we said that the electron is said to be with something with a Q. Does anybody recall what it's called? Where is it?
Quantum leap? Jump?
Well, we had the quantum leap, but it was some other term. Quantized. That was close enough. I'll accept that. We said the electron is quantized. We are restricting its value. Now, you're absolutely right. The way the electron makes the transition without existing between the space is actually referred to as the quantum leap. But we say the electron is restricted with its value, so we say the electron is quantized in this case. So if we give the electron its quantum, and say that quantum is the amount of energy needed to promote it up to its 2s, then I'm no longer going to say that the electron is in the ground state. Instead, we say in chemistry that the electron is in the excited state. But if you think about the electron in the excited state, it's like, whoa, wait a second. I'm violating the off-ball principle. I can't exist up here. So what it's going to do is it's going to very quickly transition itself right back down to the ground state in this case. And when it does, it is going to emit what is called a photon. Now, if you look at it closely, we had a quantum that came in. So here goes my wave that kind of came in. And that quantum had a certain amount of energy associated with it. So I'm going to go energy of quantum. So I had this this wave, and it had a certain amount of energy. And once again, we call it quantum. Quantum is just saying, hey, it's the energy to kind of push it up, to make it go up to one of these higher energies. When this electron jumps up, takes in the quantum, and then jumps back down, then it's going to release the energy. And that energy is going to be in the form of the energy of the photon. And that's that wave that's coming off. That wave has a certain amount of energy associated with it. What can you tell me the relationship is going to be between the energy of the quantum and the energy of the photon for this relationship here?
They're going to be equal.
Absolutely. They are going to be equal to each other because that's the exact same amount of energy. One is going up, one's going down, but yet it's still the exact same amount of energy. The one thing I want you to take into consideration is when we use the term quantum, quantum is always simply saying, I'm putting energy to cause it to go upwards. A photon is simply saying that's the energy as it goes downwards in this case. It's kind of like analogous to the Q negative and Q positive. Well, negative, the energy is flowing out. Q positive, the energy is flowing in. We just use quantum to say, oh, it's going up. Photon, oh, that's the energy it releases when it goes back down. Now, when you look at the notes here, it says right here, the quantum of energy absorbed is equal to the photon or photons of energy emitted. Well, if you look at it, the energy of the quantum is equal to the energy of the photon that's being emitted. But you'll also notice that I said plural as well. It is possible for you to actually give this electron enough energy in the form of a quantum to take it to a higher sublevel. Maybe it jumps up here to the 2p sublevel. Well, when it jumps down, it has choices here. It's possible the electron might jump all the way back down. In that case, then the energy of the quantum would be equal to the energy of the photon. That's fine. But that's not the only way that it can transition itself downwards. If it wants to, it could do something like this right here. It could jump from here down here. Now, when it makes that transition here, then what has to come out is I gotta have this energy of a photon. In this case, I'm just gonna put parentheses 2p going to 2s. That's the photon that represents that transition. And then what's going to be happening is the electron will now jump from here down to the 1s. So it'll jump down here. And when it transitions down there, it's going to emit another photon. And that would be some energy of the photon. And we'll call that, once again, 2s going to 1s. But what I know is still, the sum of these two photons still have to be equal to the energy of that quantum. It's analogous to me saying, hey, I'm down here and I jump up here. Okay, it took a certain amount of energy for me to jump there. Well, if I jump here and then jump down, I'm still releasing the exact same amount of energy that it took for me to jump up to that top rung of the ladder in this case. Now, I have one student who said, hey, you know what, Mr. Elson? Could we change this and just make it as a mathematical relationship and say that, hey, the E of the quantum, and this was in an earlier class, it said, hey, we could just express it as being what?
Equals E photon.
Directly proportional to E quantum or E photon sigma.
I could go E photon. I know E.
Sigma.
That's what I was looking for.
Oh, alpha.
That was it. I heard you. I heard you say it. I didn't hear it initially, but then I finally heard somebody say it. But isn't that what we're saying? Is that the energy of the quantum is just equal to the sum of all the photons that are being emitted in this case, and it stays the exact same thing. If I have 5 photons, then I'll just add up all their photons and energy, and it's got to be equal to the energy of the quantum that kind of promoted it up in this case. All right, on the next slide here. Only thing this slide is doing is just simply saying, hey, don't forget, quantum. Quantum is simply the amount of energy required to promote the electron up to a higher sublevel. Photon is, once again, the amount of energy that's released as it drops down to a lower sublevel. But when we talk about the energy, both of these energies, whether it's taking it in or dropping it down, happens to be in the form of electromagnetic radiation. Now, the question I have is when you think about electromagnetic radiation, do you think happy thoughts or do you think, you know what? I want nothing to do with that whatsoever.
Okay, happy.
Happy? Really? You're kind of excited? So if you were exposed to electromagnetic radiation, you'd be like, yes, give that to me, I'll take it all day long.
Bring it on.
And then you'd be like, no, you probably say, no, I don't want that. You keep that to yourself, Mr. Harrelson. But you know what Mr. Harrelson's gonna do. I can't keep it to myself. Now, I will keep it to this classroom to make sure that nobody, once again, in the hallway is exposed to this electromagnetic radiation. Basically what I got up here on my desk up here is I got this high voltage source device up here. Then I got this gas tube right here that I will put in here. I will turn on the energy. And when I turn on the energy, it's gonna give this gas inside of here the actual quantum of energy. The electrons are gonna jump up, they're gonna jump down, and when they jump down, they're gonna be like, hey, here comes that photon at you in the form of electromagnetic radiation. Now, if you look at it, I have this thing where it's pointing this direction. Not towards me, but towards you. Then, also, for safety precautions and safety concerns, because I don't want to be exposed to it, I'm gonna turn it on down here.
Wow.
Anything happen? Nothing?
Oh,
Oh, man.
touch it and it like goes into the
No.
You know, like the plasma lamps, like the bulb.
Oh, those things. It kind of does look like that. I know exactly what you're talking about. Wait a sec. Wait for it. More electromagnetic radiation's coming at you. Oh, no, it's bad. No, the kids, not all forms of electromagnetic radiation are bad. To give you an example, visible light is a form of electromagnetic radiation. Don't write this down because eventually we're going to look at all the different forms. I'm just telling you off the top of, just telling you really quickly. Radio stations like Hot 99.5, they're broadcasting right through this classroom. So their wave is traveling through that wall, through you, through me, and going right out the wall. My body is like, I'm not tuned to that specific frequency. Just like the electron is like, hey, I'm not accepting that quantum. My body's like, I'm not accepting, in this case, that actual quantum of energy. So it's just traveling right through us in this case. Microwaves are an example. What else do we got out there? We've got X-rays. Now, you might be familiar with X-rays. Yeah, X-rays do have some energy. Those you gotta be careful with. But even X-rays, if you think about it, this is something I've seen before. Have you ever seen a video where you see this little kid, he's in the dentist, and the dentist is about to give him like an X-ray, and the kid says, excuse me, is that dangerous, the X-ray? And the dentist is like, nah, it's not dangerous at all. And then he's like, stay right here, young man. And then he goes all the way around the corner behind the wall and he pushes a button or whatever. I mean, that's kind of like this little kid is like, wait a second, you just told me it's not harmful. But yeah, you're running all the way around the hall, around the wall back here, and then flicking the actual X-ray on. Why is the dentist running in this case, running away and kind of hiding?
Because he doesn't have like the vest to protect.
That's more. Alex.
He's like doing it a lot of times a day.
No, that's the problem.
Exposure.
The exposure. How much you're being exposed to it. So if you're exposed to it just for a very short duration of time, not a problem. But because he's dealing with it every single day, he's trying to cut down on his exposure. All right, now let me point one thing out to you, because this is where things get really interesting. I just told you that this light right here, and also this light right here, is being produced by the excitation of electrons. So electrons are taking their quantum, jumping up, jumping down. Here comes the light at you. Inside this tube, when you look at the actual label, the label says that it's hydrogen here. Hydrogen, once again, when I run the quantum, and the quantum is coming in the form of electricity here. Just like here, hey, if I want to not give the gas in those tubes quantum, I just cut off the quantum. If I want to give it the actual energy, it's, hey, I feel the quantum jumping up, jumping down. Here comes that actual wave in the form of light that's hitting your eyes. Now, if you think about going back to this orbital diagram for hydrogen, basically what's happening with this tube right here is the electron is like, hey, you gave electricity, you gave me actually my quantum I need. I jump up, I jump down, here comes the photon. But as soon as it jumps back down, it's like, whoa, wait a second. The energy is still there again. So what does it do? It says, oh man, I gotta jump up again, jump down. Oh, it's still there. It keeps on jumping up and jumping down until I turn this thing off. Which means that when you look at this light, it's not continuous, it's flickering. It's like here, 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 as it jumps up and jumps down. Now, when you look at the light, you're gonna be like, wait, come on, Mr. House, I'm not buying that. Because when I look at this light, I can see it as being continuous. I do not see it flickering. There's a problem. It's flickering at such a fast rate that your human eye can't detect the fact that it is flickering. Now, you might say, well, I can't see it with my human eye. I'm not sure if I'm willing to buy this, Mr. Olson. So what I did is I actually took what is called an Arduino. These Arduinos are really cool. A lot of cool things you can actually do. And this is the Arduino right here. It's a microprocessor. And basically what you can do is you can program it to do some really cool different things with it. I was telling one of my classes that my son, back in middle school, he worked with, anybody ever heard it? Nobody's heard of this thing. It's called Destination Imagination, DI.
Wait.
Nobody's ever heard of it? But basically it's like a big science competition that they actually have. But for his middle school science competition, what he did is him and a group of students, they actually used this microprocessor. And what they did is they were able to actually hook up a sensor to it, which was a motion sensor. The motion sensor would feed into the microprocessor, and whenever there's motion, the microprocessor would say, hey, I detect motion. And then what it can do is it says, hey, once I detect motion, the code says, now turn this water pump on. And what they're able to actually do is actually create a little faucet that would work based upon you put your hands close to the actual sensor, it turns the pump on, and water comes through. For this Arduino, I just programmed it, not so fancy, just to turn that light on. But it's gonna turn on at a rate in which it's gonna actually flicker in this case. But when you look at it with your human eye, you're gonna notice that it's not flickering. Then you're gonna say, well, how, Mr. Olson, is it flickering? I'm gonna show you how you're gonna detect that it's actually flickering. Point out, normally Arduino's here at Visitation, when we have Arduinos, it's normally for science fair experiments. Like this one I have sitting right here is a science fair experiment, which is a pretty cool experiment. There's a lot going on with this thing here. But basically what this particular student is doing is she has her Arduino that will hook up to some sensors that are on this tube, and then also it's gonna hook up to this coil here as well. And the object is basically you'll have this piece of metal that will go in through the tube. This coil is gonna be turned on. And when it's turned on, it's gonna produce a magnetic current. So it produces almost like a magnet. It's gonna suck the metal up in here. There's gonna be a sensor right here that says, oh, once you detect the metal, turn this coil off, turn this one on. And what's gonna happen is gonna shoot it through here. This one's gonna turn off, turn this one on, it's gonna shoot it through here. And each time it's gonna continuously speed the metal object up. And the purpose of this is they're actually looking at things like this with NASA when they launch things into outer space. Instead of you having to use all that expensive fuel to launch a rocket, why not use, in this case, magnetic coils to simply shoot one, get it faster, until you launch it into outer space. But this is kind of her project that she's working on. Pretty cool project. But what I'm gonna do for right now is show you the one that I have sitting right here. I'm gonna plug it in. I don't believe I pulled any cords out, which I must have. Which one did I pull out? It's not turning on. Ah, this one came out. There we go. All right, so if you look at it, basically what we got going on here is we got a light. Can we agree that light doesn't look as though it's flickering, right? Okay, so what you're gonna do is you're gonna get your iPad and you're gonna turn your iPad to video. So turn the video. And when you turn the video, you're just gonna hold your iPad up here, kind of point it towards the light. And what you're gonna notice is that it's not flickering, is it?
When I zoom in, is this?
But if you go to slow motion, go to slow video where it says slow, and then point it, then hopefully you're gonna notice that, you notice it?
Yes.
It's flickering. It's just, once again, with our human eye can't see the fact that it's flickering on and off because it's happening at such a fast frequency. But once again, with the iPad, if we put it on slow motion, you can see literally the fact that it happens to be flickering. Now, one thing that you can't do is you can't hold the iPad up to the light in the classroom and see the flickering. And the reason why is that that thing is flickering at a much faster rate. Even with this light right here, I programmed it to actually flicker at 5 microseconds. Now I can program it really quickly to flicker if I want at 1 second. That's very easy to do. I can also make it flicker at a faster rate as well, to the point where if you had your iPad and it was pointed here, you wouldn't see it flickering. But once again, this is what's taking place with electromagnetic radiation, especially when it comes to visible light. Yes?
Can I go to the bathroom?
Absolutely. All right, here we go. Let's continue on here. Let's unplug this, and we're going to go here. So we're going to talk about electromagnetic radiation. And here goes our wave that's sitting right there. So what we said is when it came to electromagnetic radiation is simply going to be energy that travels in the form of a wave. So here goes our wave, and once again, it's carrying energy on that wave. Keep in mind that when it comes to electromagnetic radiation, it travels at the speed of light inside of a vacuum. But for us, we're just going to say it travels at the speed of light. And the speed of light is actually given the symbol C to represent it. And we'll see it in an equation eventually, but simply C can stand for the speed of light. And when you look at the speed of light happens to be 3.00 times 10 to the 8th meters per second. You can't say it's 3 times 10 to the 8th meters per second. It's an exact number in this case, so how many zeros you have here is not going to change anything. It's like a constant. Now, to give you some perspective on how fast it happens to be, if I have this red expo marker, and say that it just took off at the speed of light, and I just simply counted how many times it passed my hand. And keep in mind, to pass my hand means it has to go where? So if it's traveling this way here,
Circle?
the circle around the what? The earth, right? And then eventually it'll come right past my hand again. If I count at the speed of light, it will go past my hand 7 times in 1 second. That's how fast the speed of light happens to be. It's extremely fast. Sometimes we look at the magnitude of the number, we can't appreciate just how big that magnitude happens to be. And we're going to see that ramification as we start doing some calculations as well. So what we're going to do really quickly is we're going to talk just really quickly about things that you should have learned in conceptual physics. And that's just the anatomy, in this case, of a wave. The top of the wave is referred to as the crest. The bottom of the wave is referred to as the trough. Going through the middle of the wave is referred to as the origin in this case. And then going from the origin all the way up to the crest is known as the amplitude. Or going from the origin to the trough is also the amplitude as well, because the wave happens to be symmetrical. Now, this is a good question. Going from this line to that line, back in conceptual physics, was known as what? The wavelength. And it's a distance. It's a measure of distance from wave crest to crest, or we could say from trough to trough. And when we look at the wavelength is given the Greek symbol, lambda. And lambda just kind of looks like this right here. There we go, we got lambda. And lambda, since it's a measurement of distance, is going to be in units of meters. So wavelength is in units of meters. Easy enough. The other thing we're going to talk about is frequency. Frequency, when you look at it, is going to be the number of waves that pass per unit of time. In this case, our unit of time is going to be seconds. So if we look at the example that I have right here, I got 3 different waves. And what we're going to simply say is that if this is my hand, and I count for 1 second, 1001, then what I can see here is that I get how many waves? Let's see, that's 1 wave, 2 waves, 3 waves. But wait a second, I have also half of a wave sitting right here, and also half of a wave sitting right there. So I get 4 waves that pass my hands per second. Here I get 1, 2, 3, 4, 5, 6, 7, plus I got the half here, plus I get the half right there. So I got 8 waves that pass my hand per second. Here I got 16 waves that pass my hand per second. So when we talk about, once again, frequency, it's just how many waves pass per second. Now, for us in this class, when it comes to frequency, we're using the Greek symbol nu. And nu is nothing more than kind of like a fancy V here. In conceptual physics, you use this right here, F. Typically, F is not used as frequency. Most textbooks, you're going to see this symbol right here, the Greek symbol nu used. The reason why I suspect that your textbook used that instead of this is because quite possibly in conceptual physics, you would confuse that with being what? Velocity, exactly. Luckily in chemistry, we don't really have to deal that much with velocity in this case. So we'll be using, once again, that symbol to represent, in this case, frequency. When it comes to frequency, once again, the number of waves per second, which is expressed 1/seconds, but 1/second is the same thing as simply saying hertz. Typically, you'll see me write it as 1/seconds because I like to see how my units are going to cancel out. But you can write it as hertz as well. Now, one thing I want to look at, and you can help me out here. I want to look at the relationship between, in this case, frequency and also wavelength. Look at what's going on here. When I have really long wavelengths, I only get very few number of waves that pass. As I go with really small wavelengths, then I get a lot of waves that pass, which means that frequency and wavelength are directly or indirectly proportional to each other? Indirectly. So there's an indirect relationship that exists between the two in this case. Okay, well, if that's the case, then watch what I can do here. I can do this. I can write it as a mathematical expression. I can say that the wavelength is inversely proportional to the frequency. So I've got that. But then also, I remember back in the gas law chapter, we learned how to get rid of that proportion sign and make the two equal by introducing what? A constant, exactly. So I can go in here and simply say, hey, the wavelength is equal to a constant times 1/the frequency. And when I look at it, if I solve for the constant, I can say that the wavelength times the frequency is equal to a constant, which I'm going to call C in this case. I'll just spell constant out. Watch what's going to happen here. Wavelength, we said it's going to be in units of meters. So hey, that's in units of meters. We said that frequency is in units of 1/seconds, which means that the constant is going to have to be in units of meters per second. And if I remember from conceptual physics, meters per second is a unit of what? Speed, right? What is this right here?
Speed of light.
Speed of light. That's why I put the C there, not just because it's a constant, but that is the speed of light. Which means that when it comes to electromagnetic radiation, if I know the wavelength and you ask me to find the frequency, no problem. I got the speed of light, I got the wavelength, I can find the frequency. Or vice versa. So this is, once again, just an equation that will allow me to be able to figure out the frequency or the wavelength for any given light. Now, what I need to do is one problem here. It's 2:30 Tuesday. We're going to do this problem really quickly. Here we go. Hot 99.5. What we're going to do is we're going to see if we can figure out what the wavelength of hot 99.5 is going to be. So wavelength is in question. So what we got to do is realize what hot 99.5 actually represents. Hot 99.5 is on the FM stations. All FM stations are broadcast on 99.5. They're on megahertz. Yeah, so if you ever listen to radio stations from now on, sometimes some radio stations will announce like we broadcast on 99.5 megahertz. AM radio stations broadcast on kilohertz, but that's okay. Keep in mind, I cannot substitute in right here. I can't substitute in megahertz. That is considered to be hertz right here, which means I gotta first start off by converting this megahertz into hertz. So I'm gonna go in and simply say 99.5 megahertz, do my dimensional analysis and go in here and say that for every 1 megahertz, and I remember mega millions, which means I gotta have 1 million of these hertz to be equal to that megahertz, which means I'm gonna get something that looks like this here, 9.95 times 10 to the 7th hertz. And a hertz, once again, I'm just gonna put it as true units of 1/seconds. Now I'm ready to solve this problem. Because now I can go over here and say, okay, let's see what's going on here. Wavelength, that's my unknown. The frequency is 9.95 times 10 to the 7th, 1/seconds, is equal to 3.00 times 10 to the 8th meters per second. And then we're getting lambda is equal to 3.01 meters. Where's my meter stick? Ah, here it goes. 2 meters, 3 meters. From crest to crest. So roughly about that. That's what we're looking at. Hot 99.5. That's the wavelength that's being broadcast right through this classroom. But the question I have, we got 1 minute here. How many waves would pass my hand in 1 second? How many of these waves, 1001, will pass my hand in 1 second? Better yet, what am I asking you in this case? How many waves are passing my hand per second? I'm really asking for the what?
Frequency.
The frequency. 99,500,000 waves of this length is passing my hand every 1001. 99,500,000. That's a lot. But once again, it's due to the fact that this thing is moving at the speed of light. Homework assignment is up on